We carried out simulations to dimension solar powering for a sensor entity. Is that method reliable? In this episode, I will compare the simulation with real-world measurements during the critical season. Today, we want to follow up the actual experience with our autonomous outdoor sensor that we simulated earlier to predict the performance and to dimension the desired solar powering. In the earlier episodes, number 1, 2 and 3, I explained the dimensioning of this arrangement. In addition, I carried out a number of tests with LoRa, which I also shared with you on this channel. First of all, I'm happy to tell you that the little device made it up to here. It is working now for more than 300 days outside in the sun, rain and snow. There was no outage at all. It delivered its values via LoRa every 3 minutes over the whole time period. Remember, for our experiment here, we used only half the solar panel size, which we dimensioned with our spreadsheet tool. We did that on purpose because we want to compare how accurate our predictions are when we use the actual solar yield that we had in the given time frame. For this purpose, we want to compare the state of charge of the battery, especially in the critical season. On our agenda today, there is a short recap of our simulations that we carried out to dimension the solar powering. After more than 300 days in operation, we can compare the performance that we actually experienced. We will use the actual solar yield that we had in the time frame in order to judge about the accuracy of our simulation. In addition, I felt it would be good to look at some other years' data and to have a discussion about variations which can occur. Our early predictions were carried out using a worst-case assumption for the solar yield in my region. That was the best we could do because we wanted to design a reliable solar powering. Here is the original simulation that we computed for an 88 cm² solar panel and a 3000 mAh battery. The black line is our expectation, the dashed red line is the best case, and the dashed blue line indicated the worst case. For the computation of our simulations, we had to make a number of simplifications. This was important because the method shall be applicable for everybody using easy means. Now, of course, it is interesting to check the actual accuracy of our method. We go to our spreadsheet tool, which I updated by the actual solar yields from the time frame where we have the real-life experience. I also made some minor error corrections and added some interesting simulations together with the solar years from earlier years. A good friend of mine, who is living just 10 kilometers from here, operates an own professional solar generator. He provided me with the accurate solar yield data. I think it is fair to say that we have now a better database concerning the actual solar yield compared to the previous version. As always, you can download the tool and use it for your own projects. There is a lot more to discover in the tool. However, here I'm just concentrating on the aspects for the comparison with my measured data. We go directly to the sheet where we simulated with the actual solar data from 2021 using only one solar panel with a size of 44 centimeters square. You know, for this experiment I decided to use only half the panel size so that we could better judge about the accuracy of the computation model. For this purpose, especially the falling and rising slopes of our battery state of charge simulation are of interest. With a dimensioning that is far on the safe side, we would possibly not see any slope, because the battery would remain always fully charged. Okay, we concentrate now on the falling slope in November and December, because we can compare this area with our measured data. The simulation predicts us that our sensor will practically stop working at the end of December, because the battery gets too low then. Let's see what we actually measured with the real outdoor sensor entity. We look at the behavior of the battery voltage in the time frame mid of November to end of December. The orange curve shows us the battery voltage of the outdoor sensor. The light blue curve is the battery voltage of an identical indoor sensor that I had to charge several times during that period. The orange graph is showing us that mid of November the voltage dropped already slightly under 4 volts, which corresponds to less than 90% of charge. The ripple is caused by the charge up from the sun that appeared occasionally during this period. At the end of December, the voltage dropped to 3.1 volts and the outdoor sensor entity stopped working. I think this is interesting. It is really close to what we predicted with our simulation tool. Cool, isn't it? Although it is not 100% accurate, our simulation method seems really recommendable for the dimensioning of solar powering in that field. Now, just to complete what you might want to know. We look at the new simulation with 2 solar panels. And as expected, this would have worked well over the last winter season. The solar yield of the last winter was rather on the low side. But we could even introduce a variation of minus 30%, as we can see from the next simulation. And in case we still want to increase the security further, we could add a second battery. With that, we should be prepared for the absolute worst winter. Our learnings and the summary. When we use the actual solar yield, our simulation comes pretty close to the reality. This doesn't go without saying, because we had to make a lot of simplifications and some of the parameters we had to estimate. Our chosen arrangement works safe with the smaller panel from February to November. However, it needs definitely the bigger panel to overcome the winter. We expected this before, thanks to our simulation tool. Finally, I can give some hints which were not so obvious to me when I started this journey. I found out that thin film solar panels are good for low light conditions. Even when their efficiency is not as good as for the other options, they are probably best to overcome the critical season, because you can benefit more from diffuse light. It is best to adjust your elevation angle to the winter sun and your azimuth angle according to the free sky that your solar panel is seeing. You can do this because usually you still get plenty of energy in the summer season. And you get also the positive side effect that because of the steep angle, snow will not remain on the solar panel. In a nutshell, you just need to optimize for the bad months, where you get the least sun. Hope that was a bit enlightening and you can use the tool for your own purpose. Maybe a final word on the episode. As an engineer, it is always good to understand where the limits of systems are. This is important for technical and for economic reasons. You can save money for your tinkering projects, or in more serious cases, it can be the basis for the commercial success of a project. By the way, this remembers me that I had in mind to try out a low power board for my sensor module. In this context, you might want to see the earlier episodes about solar powering and battery state of charge. Now, stay tuned and don't forget to subscribe and support the channel. See you soon in the coming episodes.